This is the final introductory video for a first course in modelling, analysis and control, and the focus here is on core content and organisation. The first videos then introduce the concepts of systems, behaviours, performance and the role of feedback to control behaviours. So this last video is going to cover the organisation of a first course and the core skills that you will need. Summary then. What skills do you need in order to control the behaviours of the engineering systems around us? The most important skill is the ability to quantify behaviour, and secondly, to quantify how changes in parameters will affect that behaviour. Now, this is the main technical content of an introductory control course. We will learn and apply the basic mathematical skills and techniques you need to analyse and design system behaviour. And you might notice here that feedback is almost a secondary issue. We should also note that it's taken for granted that laboratories and industrial case studies and context are of course important, but we're not going to discuss that sort of detail as we assume they will happen automatically. Mathematical requirements. The following slides break down the mathematical requirements into more specific skills so that you can basically have a list in your head of what you need to do. An introductory course should not require analysis and mathematical skills beyond first year undergraduate level. So the focus should be more on concepts than detailed mathematical rigour. Yes, you do need some maths and you do need some rigour, but it should not be excessive. If you need higher level mathematics, it's likely to be in a second or more advanced control course. Now, this summary I'm giving here basically is based on an international survey of what the community has accepted as being important. Clearly, different institutions are going to add to this list other aspects depending upon the year group where they give this course. The speciality, are you mechanical, electrical, chemical and so forth? What earlier learning have you already done? And of course, the size of the course. Is it 20 lectures, 40 lectures or what? But we should note you cannot cover everything in one course. And so what we're going to give here is the basics only. Modelling continuous systems. We need to be able to represent real systems and their behaviours using mathematical tools to enable quantitative analysis and design. So how do we do that? We've got to be competent with first principles modelling of low order linear systems, and the emphasis here is low order, so nothing too complicated. We need to understand how to represent systems models using ordinary differential equations. We should understand the analogies between models of different systems, so analogies between electrical systems, mechanical systems, chemical systems, and so forth. And the analogies are almost obvious from the underlying mathematics. We need to understand how parameter changes the models. So if you change a spring, how will your model change? If you change the volume of a tank, how will the model change? And so on. Now, some courses might also cover state space models or a brief introduction to non-linear models, and that really depends on the emphasis in your department and how much space you've got. We should also emphasise that increasingly discrete models are becoming important industrially, but there's a problem that a first course can't cover everything, so it's highly likely that this will be omitted simply because there is not enough space. Solution of ODEs. System behaviour is strongly linked to solutions of ODEs, so students would enhance any study of this from their mathematics modules. So the key point is you've probably studied these in your maths modules and done it as a maths topic, but now you need to change that and think of it as an engineering topic. So we're going to start with what you've already done, analytic solutions of first and second order ODEs. Implicitly, you could do higher order, but we might not bother too much because that doesn't add a lot of insight. Analysis. So the focus next is on interpreting the solutions that you see. So thinking like an engineer. What behaviours can you see? Can you characterise certain patterns in the behaviours that are linked to the parameters of these ODEs? Evaluation. How do system parameter changes impact on the behaviour? So if I change the spring, how does that change the ODE? and therefore how does it change the solution and the behaviour that I'm seeing? Design. How do I make parameter choices to achieve desirable behaviour? So you can see basically here we're building up the skill level as we go. Now advanced, it's unlikely that this would be an introductory course, but ultimately where you're moving is how do I design an overall system? How do I select the components? How do I select the interconnections in order to get the behaviours that I want? Laplace transform tool then. The Laplace transform is not essential in the first course, but the international community would say it's recommended, convenient, and allows simple insight into behaviours and design, so it's typically used. The focus in a control course should be on using the tool rather than getting too hung up on first principles derivations. So what do you need to be able to do? Laplace and inverse Laplace. Inverse Laplace involves partial fractions. And emphasis here is on common signals, not weird signals that you might get in a maths course, which is testing more rigour. Solving ODEs using Laplace tools. Definition of a transfer function. What does system gain mean? And understanding of linearity and superposition. And block diagrams. Behaviours then. So we're going to use ODEs and Laplace transform tools to quantify and classify behaviours. So you need to understand the role of poles and how you might infer system behaviours from a transform, including the final value theorem. You need to understand concepts of stability. What's the significance of the left half plane and the right half plane? And what happens if you have systems of transfer functions, so systems interconnected with each other, and how might you draw block diagrams to represent these? Introduction to feedback. The course will have established open loop behaviours are often poor. So next we want to introduce tools to improve those behaviours. So first, make sure you understand the weaknesses of open loop control and therefore the importance of feedback. And in fact, that was done in the introductory videos. Next, you need to know how to build simple feedback block diagrams and closed loop transfer functions. So how do I represent feedback using a block diagram? Having done that, you want to quantify and compare open and closed loop behaviours. And there's a number of different words here that you need to become familiar with. What's an offset? What's a pole? What does stability mean? What's a time constant? Damping, disturbance rejection, and so forth. And these are the sorts of words you will use to quantify your comparisons. And ultimately, we're moving towards doing a simple feedback design. So how might you design a proportional feedback or a PI feedback? Now, if time allows, and that depends on the size of your course, you might do more systematic PID design, but an introductory course is unlikely to have space for that. Software tools then. Now, as a professional engineer, you're going to use software to simplify tasks as much as possible. The same applies at university. Don't do on pen and paper what a computer will do for you. However, it is important to do the pen and paper exercises a few times just to make sure you understand what's going on. For the author at many universities, it's assumed that you'll be using a tool like MATLAB. And so whatever tool your university is using, get it on your computers today and start using it. Now, most of you will be taught these tools formally outside of the control course. And in fact, the control course will only need very limited functionality. And you'll see I've put a link down here which summarises the functionality that I think you will need. And if you look at that website, you'll see it's very few functions. So conclusions. This video has outlined the content of an introductory course in modelling and control for engineering undergraduates. The focus has solely been on the core requirements, what you really must cover. Now, each institution will vary and or build on these core requirements according to how big is their course. What background have you already got when you start this course? What's your discipline? What year is it taught in? And other internal priorities. But likely the bits they add will be relatively small by comparison. Now, a notable omission from these slides is frequency domain methods, and the reason for that is these require more advanced mathematical skills and so would typically be in a second or much larger course.